go to the numerical techniques. So one possibility is here we can go, you see, and then slow down a little bit, and we can have more discussion if that could be possible. If you know anything, have any question, just ask me. So numerically, you see that you see all those models. You need to minimize with a curve. You see all those models you need to minimize with a curve. You see here you minimize with a boundary. You see that how do you see really minimize with the boundary or minimize with a curve? And that's a numerical technique we are going to talk. So therefore, the first method we are going to talk is how to minimize with a curve or boundary is the level set methods. So the level set methods, you see that it's really, you see already is a classical. That's mostly due to Xue-Cheng. I think many of you know level set very well. Maybe you have been testing with level set. So the level set methods is essentially, you see that I want to move a curve. A gamma, most level set can deal with a closed curves. It cannot deal with an open curve. If an open curve, you must play with the special techniques. So level set, you need to deal with the closed curves. So if you want to deal with the closed curve, so therefore you see that snake model directly move the curve. You put many points on the curve. You put the endpoints on the curve, and you move the curve by such a formula. That's an explicit method. You move the curve, snake model. So the weak point of a snake model is, you see, one is the merging and splitting of the curve. That's getting very difficult. You cannot simulate very complete curve. There's other difficulties that you see that. Suddenly you see that for some application, you see those points may suddenly get very dense in one region and very sparse in another region. And then you get problem to trace a curve. You may need to increase the points somewhere. So those are the difficulties. So the level set methods is that you give a closed curve and then define a distant function such that this function is the distance to this curve. And then there's one-to-one correspondence between gamma and the function phi, right? So for any given curve gamma, there's a unique distance function. So there's one correspondence. So if you get this phi, you get this curve. So the level set method that when you want to minimize this curve, and you must move around to see which minimize the image, right? But the level set method is that you don't move the curve, you move the level set function. You move the function up and down, and that produces different curves. So therefore, originally is a minimization problem with the gamma, and then you transform it into a minimization with this level set function. And that's essentially the level set idea. So therefore, it's like this one, you see that you have a distant function. So you see you move the function down. So therefore here you cut it by the zero level curve. And this is a boundary, this is region, right? You move the function down, and here you see that these two regions are going to split. You move further down, you get two other regions. So I think this is the essential advantage of the level set methods. You see, splitting and merging is very easy. So you see from here, you see when this point is splitting, you don't need to do any surgery. But if you use a snake model, you see this point, you must do a surgery here. Also when the level set come together. So this is essentially the level set method. So original minimization with a gamma, with a curve, you become a minimization with a level set function. And here mostly we require is a distant function. So it's a distant function. But some application like the segmentation methods, you don't require a distant function. Any positive function, positive inside, outside is enough because I only need the curve. So inside you may get multiple values, just if you produce this curve is enough. But so for some other application, you need to enforce this distance condition. And this is I think Stan Osher's most favorable work, and this is very influential, right? So therefore you see that how do you move a level set? As you have one level set, mostly you have one curve. But mostly, you see, let's say we want to move the curve, so which means our curve depends on time t, right? And also you see that this is S is a parameter ratio in the snake sense, t is the time, so therefore S goes along the curve. When t moves, the curve move up and down, right? So therefore you see that assuming this is gamma t, this is the corresponding level set function. You also add the t here. Originally we only have x, right? So therefore you see that if you want to move this curve, what kind of movement you should have on the level set function t, right? So therefore, originally you see the snake model move the curve, but use the level set method, we don't move the curve, we move the level set function. You see that what kind of if one movement of the curve, what kind of corresponding movement you must have on the level set function. So this is essentially, I think this is well known. You see, every people who has been working with the level set, you know about this one. So therefore, you see that. So this is a curve, and phi on this curve equal to 0, right? And so therefore, you see that this curve originally this parameterization with the level set, and this curve expressed in this way. So therefore, if you differentiate this one on the curve, this function with t, so assume in 2D, so here you get gradient, right? Inner product with xt, so that's coming from, and then you get phi t, right? So if you differentiate with t, and that's what you get. Assume you see that in a snake model, you want to move the curve with a velocity equal to this one. If this is the velocity of the curve, right? So therefore, if this is a curve, and so every point I move it with the velocity t, and so this will be the movement in the original snake model, right? So therefore, if you put this one into here, so you get vt equal to this one. We know that so this vector is what kind of vector for the zero level curve? This is a unit normal vector. And so therefore, if you inner product with this velocity with this one, this will be the normal velocity of the curve. So therefore, you have arbitrary v. So this will be vn. So this will be v tangent. This will be v tangent. So therefore, you see the tangent velocity, the tangent movement doesn't change the curve, right? You just make the curve running around. Only the normal velocity changing the curve. So therefore, you see that when you give a velocity, so you shouldn't do anything. You should just use the normal velocity to move the curve. So therefore, if you define this one as a normal velocity, so therefore, if you put it there, here should be plus. Here should be plus. So therefore, you see that if you want to move a curve with a normal velocity Vn, so here should be plus. So therefore, it's equivalent. You need to move the level set by this equation. So this is a well-known level set equation, right? If you want to move a curve with a normal velocity Vn, you just solve this one, and then the corresponding zero level set will be moved according to this velocity. So this is a well-known level set. This is a stanza, is the first invention, right? But there should be Vn there. So this is the level set methods, right? Also, you see that if the level set is given, so therefore this will be the unit normal vector to the level curve, including zero level curve, and this will be the curvature. If the curvature for the zero level, so therefore you can easily, if a phi is given, you can easily compute the curvature. If phi is a distant function, and this reduces to the Laplacian of phi, why? If phi is a distant function, the curvature is just the Laplacian function on the curve. Why? Yeah, if the distant function, and this will always equal to 1. So therefore you see that, and then you just reduce it to the minus Laplacian, so you can easily calculate. So therefore also from the level set function, here is a Heaviside function. Heaviside function where phi is bigger than 0, Heaviside equal to 1, less than 0 equal to 0. So this will give the area of the positive region. Yeah, so here you see that the Heaviside phi is a characteristic function of the region, right? So therefore, this is what we talked yesterday. If you calculate the total variation of the characteristic, this gives you the length. This is gamma is a boundary of D. So therefore, another way you see here, you can write it like a delta phi. This is very informal. This is very informal. Very informal. So therefore, you see that if you know the level set function, you can get all those geometrical quantities. So the area, the length, the curvature, the normals, and you have everything. You can express everything of those things by the level set function. So therefore, you see, originally, you see many problems. We need to minimize those things. If you transfer everything to the phi function, and the original minimization on phi, it becomes a minimization with the level set function. So this is essentially the level set idea. You see, for some applications, you need to really enforce a distant function. You enforce a distant. So therefore, enforce a distant function is essentially based on here. So given closed curve gamma, the distant function is a viscosity solution of this equation. So this is essentially, you see that phi x squared plus phi y squared equal to 1. And this phi should be, you see that mostly this gamma is a given. Phi equal to 0. In the rest of the region, you should satisfy this equation. The distant function is a viscosity solution for this equation. You see, 1D is very easy to understand, right? So 1D, I think 2D is not difficult, but 1D, you see, it's a very easy to understand. So therefore, you see, in 1D, gamma mostly reduces to some points. In 2D, gamma is a curve. 3D, gamma is a surface, right? And so therefore, the distant function, you see that the distant function here, it depends on which one is near. If it's here, the distant is the middle. So therefore, the distant function, the sunny distant function is just look like this one, right? If this is a gamma, you see that if this is the interior, and this is the interior of the region, this will be exterior of the region. And the sunny distant function, this is the sunny distant function. So therefore, this function has a singularity in the middle of the region, right? But otherwise, you see this slope, the slope of this one is just exactly equal to 1 because x equal to y, right? So therefore, the slope is 1. The slope is 1. So therefore, here the phi derivative equal to 1. So here the phi derivative equal to minus 1. So phi derivative equal to positive 1. Phi derivative equal to minus 1. But the absolute value is always equal to 1, right? So therefore, you see that, so to compute the distant function, essentially you try to compute the viscosity solution for this one. And that should be enough. In 2D, you see that, in 2D, you see if this is your curve, right? If this is your curve, and then you see that, so here is you see the distance. So here is the level curve of the distant functions. So in the end, you see that you become this skeleton. So therefore, in 1D, the function is singular at the middle of the region. In 2D, the function will be singular at the skeleton. Right? But you see that essentially, you see that if you make a tangent, for every point you draw the tangent, so the level curve should be orthogonal to the tangent, and then you see if these two lines meet here, you see if those two lines meet here, this point must have a singularity. But on this curve, you see that was essentially the distance to the curve. Right? So this is, if you really need to calculate the distance function, you try to calculate the viscosity solution. So therefore, you see, mostly we use, you see, the very old methods with the standby damping Yang. We use it. So essentially, you see that they do a time marching and do a characteristic updating here. We use this one to update to calculate the distance function. And so therefore, a lot of people use the time marching, fast marching. So fast marching is essentially, you see, 2D, you start from this point, you check, you see which points are near, and you expand the distance function larger and larger until you compute the distance function in the whole region. And so those are the methods we have been using. Even this one is very easy to use. It was just characteristic upwinding. You do explicit, and here you do explicit. So mostly we use that method to compute. And that's, for most cases, is sufficient. But fast matching could be more accurate. Could be more accurate. Yeah. So in case you may need to read distance, you need to calculate distance function to a curve. Right. So therefore, you see that and the Chang-Vese method, which is one of the most popular segmentation model. I think Chang-Vese has become so popular. If you Google search, so it's unbelievable. You see that how many places they have been using Chang-Vese. You see, even there are people implement the Chang-Vese over the Samsung handset. They have a code which you can run the segmentation on your Samsung mobile telephone. That was really unbelievable. So essentially, the Chang-Vese method is essentially to solve this two-phase piecewise constant Mumford-Sharp by level set method. So therefore, piecewise constant Mumford-Sharp by two constants. So essentially, you have omega 1 C1, omega 2 C2. This is the length. You minimize the length. So therefore, you see that how do you solve it? You don't use snake model. You use the level set method. So therefore, you see that one level set should be positive in omega 1, negative in omega 2, and 0 on the interface gamma. So you introduce one level set function. So therefore, once you introduce a level set function, you see that originally minimize the gamma. How do you become a new minimization with phi? C1, C2, you don't do anything. You don't do anything, right? So how do you transfer the minimization with gamma to a minimization with phi? So this is how do you transfer. You see, the length, the Heaviside function is a characteristic function of region omega 1, right? So therefore, the total variation of this characteristic function becomes the length. So therefore, alpha delta Heaviside phi, this produces the length of the interface. This produces the length of the interface, right? And then you see that in omega 1 should be closest to one constant. So therefore, you see that this C1 is essentially C1 minus U0 squared. This 0 should be under script. So therefore, if you just put the Heaviside, you see this is 0 in omega 2. So this term exactly equal to that term, right? Because Heaviside equal to 0 omega 2. If you just put the Heaviside here, you just can integrate on the whole omega, right? And similarly, the 1 minus Heaviside. So therefore, you put the 1 minus Heaviside, and this omega 2 disappear. So here is omega, and then you see gamma omega 2 completely disappeared. And then you see the minimization with you see gamma. You can now just minimize with the phi. If you get a minimizer of phi, you get a minimizer of the original problem. You get a minimizer of the original problem. So this you transfer a minimization with the interface. You transfer it to a minimization with a level set function. So you just move this level set function. That's enough. That's enough, right? And so this is the essential point. You don't move the curve. You move the. And now you can just move the function phi. And this is the Chang-Vese methods, right? So it's really looks a very, very good idea. It looks simple and very, very elegant, right? So therefore, you see that Heaviside is just defined here. Heaviside, so the Heaviside function is essentially, you see that equal. So here is x, here is Heaviside. Heaviside equal to 1 here, 0 here, right? This is the definition. So from phi, you see that the where bigger than 0, you get phi negative, and the interface give you the interface. So therefore, this is become the Chang-Vese method, which is very easy to solve now, right? Looks very, very easy. So in real simulations, so therefore, I think the original paper you smooth this Heaviside function. So the Heaviside really jump directly from 0 to 1 here. In real application, you do a small smoothing. You replace Heaviside by Heaviside epsilon. So therefore, you see delta function by corresponding delta epsilon function, and you minimize this one. So that's what you do. That's what you do. Yeah. So here you see that if we define, so here is the C1, C2, here is the phi. We define the minimum wisdom with phi with C1, C2. So here is you want to calculate the use principle of variation, and you perturb, you see phi by epsilon mu arbitrary function. You try to calculate this one. Oh, there is a mistake. Here is a mistake. So therefore, you see, this is essentially that you try to verify. You see that if phi should minimize the energy, and then this variation must be 0 for arbitrary mu, right? If phi should minimize this function, this is arbitrary function mu. If phi should minimize this one, and then for arbitrary mu, this limit must equal to 0, right? Because when epsilon goes to 0, that's the smallest, so that should equal to 0. So therefore, you calculate the variation with phi. So therefore, you replace here phi plus epsilon, epsilon mu, phi epsilon mu, and you calculate. So therefore, you see that those two terms are very easy because this one disappear. So this one minus that one, and then you get the delta phi here. You get delta phi here, right? But then here is a mu. I have missed the mu. You have a mu here. So this you just do the simple calculation, calculus of variations. And the length term, you see that length term of variation, there is also, I miss a mu here, come to here. How do you calculate this one? Take a little time. If you want to go through it, so we can go through it together, right? So the minimization of this one become this one time of mu. I miss a mu here, and that take a little time to calculate. Yeah. Mu is arbitrary. You perturb phi by arbitrary. Epsilon is constant. Mu is arbitrary. Oh yeah, I'm sorry. Yeah, I'm sorry. Maybe I should use a mu. So here should be a phi tilde or something, right?
And then I think for the computer term, so you also need the delta function, right?
Sorry? Oh yeah, here you be over phi. Here you be over phi. Yeah.
No.
Here should be phi. Here should be phi.
And then,
Phi here, phi here.
And then times and then delta phi, right?
What? Yeah, here should be phi.
And then delta phi, and then even in the last term.
Yeah, here should be phi.
Yes,
phi.
from the fidelity term we get the delta phi, and then the first term, and then in the second, in the last equation.
Yeah, this
the
one.
last part.
Where?
No, in the curvature.
Here.
Yes.
Yeah, this should be phi.
No. Times with this term.
Yeah.
Times and delta phi, right?
Yeah, that's right. That's right. No. So let's write down the correct one on the blackboard. Yeah. So therefore, you see that f phi equal to all those things, right? So therefore, essentially, you see that we put f phi plus epsilon, maybe here, yeah, because mu is a constant, I should use another function here. Because this I did it on Sunday very quickly. So therefore, you see that there's not enough time to check.
Epsilon times eta.
Eta, yeah, eta, right. So for example, you see that, and then this is a phi ci. You see that when epsilon goes to 0, if phi is a minimizer, and this should be 0. This should be 0 for arbitrary eta. So therefore, you see that this one, for the fidelity term, is very easy. You get the delta, this one disappear. So it's here, this one is correct, right? This one is correct. So therefore, and then you will get what exactly is written there, which is C1 minus U0 square, C2 minus U0 square, delta phi. For this part, so therefore for this part, yeah, should be equal to mu delta here delta phi times eta. Yeah. How do you come from here to here? There's a little trick. It's not very obvious. It's not very obvious. There's a little trick to come to here. Yeah. But at least a variation of this one equal to this one. It's also integral, right? Right.
You need to add to the first.
Yeah, also add down here. Very good, very good. So if you do a variation of that one, so that means you see that if phi should be minimizer and this one should be equal to 0. So which means that C1 minus U0 square minus C2 minus U0 square delta function phi. Oh, here there's also, I missed a delta phi here. Here there's also delta phi. And so here is a minus mu divergence phi delta phi. This is equal to 0. If a phi should be minimized, this should be 0. Mostly, you see, in numerical, we do a smoothing here. You see, mostly in the original methods, so therefore you just do equal to minus plus. This is you move phi function in the negative gradient. So you put the minus here plus. So that will be the negative gradient flow for phi function. I think I have it somewhere here. You see that if a differential with C1 is very easy, right? If you want to minimize with the C1, you just C1 is a constant. You just differentiate, you get 2 C1 minus U0, and this should be 0 if a C1 is a minimizer, right? If a C1 should be minimized, this should equal to 0. And similarly, C2, you see, you just get the minus, but it doesn't matter, right? It just doesn't. You know, I miss also minus here. You see, that's due to Sunday. It's not because of me. So here I will be minus because there is a minus here, right? So C2. So therefore, if a C1, C2, and phi should be minimizer for phi, so this must equal to 0. For C1, C2, those two must equal to 0. And so therefore, you see how to use the two-phase transversal that you do. There is a delta phi missing here, also delta phi missing here. So you do a gradient descent on phi, use this equation. C1 equal to 0, and you see this one equal to 0. So this one equal to 0, so therefore you take a 2 away, C1, and so therefore exactly you get this formula. So C1 is equal to this one. So this is essentially integrate U0 omega 1. This is the area of omega 1. So that's just the mean value of U0 in omega 1. And this is the mean value of U0 on omega 2. So this is the transversal method. So therefore the simple way is still there should be phi here, delta phi here. So therefore you can just do explicit time marching. You see that do many iteration of this equation of the C1, C2, to many iteration of the C1, C2. So this, I think this was the original algorithm which was used in the transversal paper. Yeah. So you can see that essentially you see that you don't minimize with the curve anymore. You just turn it into a minimization with a level set function C1, C2. So if you need more than one region, and then you use a 2-level set function, you can produce 4 regions, right? You see 1 level set function where it's bigger than 0, bigger, less, bigger, and then you produce a 4 region if you use 2-level set functions. So therefore you see that if you know that you exactly want to find 4 regions and use a 2-level set function, your original 4 region thing can really be. I think here is a multi-phase transversal. So therefore you see that I give a U0. I want to segment it into 4 regions. So essentially I know I only want 4 regions, and then what you do, you see that here is your U0. Here your U0. And then you use 2-level set. You use a phi 1, phi 2, C1, C2, C3, C4. And so here will be the length for the boundary for the phi 1 level set. So here will be length for the boundary for the phi 2 level set. So that was essentially, you see that. And so the first one calculate this length. And the second one calculate this length. So you minimize the sum of those 2 lengths. And then you see that, so here is essentially, you see like, so here is a region omega 1, you see C1, omega C2, so this is each region, you see that each region you use 0 minus a corresponding constant. So this is essentially if you want to use the Chang-Wei. So now you need to know exactly you want to have 4 regions. You want to have 4 regions. If you need more than 4 regions, and then you need 1 more level set, and then that can produce up to 8 regions. 8 regions. If you use so there are 3 level sets produce 8 regions. 4 level sets produce 16 regions. So in this way, you can increase the number of level sets. You get more and more regions. But I think you see for level set, if you need more than 3 level sets, and then the calculation is becoming rather complicated, because you see that you see 1 level set. This is the equation. You need 3 level set. You need you see you have a multiplication of a delta heavy set, and those 3 nonlinear equations need to interact with each other, especially if you use an explicit you see method to solve it, and you see that may not be easy. I think we have tried 2 level set. You see 2 levels are mostly still okay. If you use 3 or more level set numerically, so that's really so could be something a challenge. So therefore you see that the Chang-Wei method, why is getting so popular, so many people use it, essentially use level set for sexual Gaussian, can handle very complete geometries. So therefore you see that this is one of advantage. It's like a snake model, you cannot handle very complex geometry. It's a region based, robust with noise, and you can segment the images. There's no edge, right? So even like this image, if you want to detect the edge, you will get something completely different. But if you use a region based, so therefore you don't use the edge information. If you really calculate the edge information of this image, detect the edges, you will get something quite different than what you get here. So therefore you see that, and I think those are the 2 important reasons why the Chang-Wei are getting so popular. So therefore then you see that still have some disadvantage. We need to get better. So what are disadvantages? Slow in convergence. Even you see you get other way to solve it, it's still slow. And then the other thing is that it's non-convex. It's non-convex. So the minimization problem is non-convex. It's convex with a C1, C2, but non-convex with a phi. So therefore you see that even in the 2-phase case, you see that the minimization with the phi is non-convex. Due to heavy set is non-convex. So with the phi is non-convex. So due to non-convexity, if you minimize the non-convex function, so therefore you see that you could easily get stuck with local minimizers, and so therefore it depends on the initial value. So this is I think this is common. So this is you segment the cameraman. So here is if this is your initial curve, you segment this man out, and this is the boundary. But if you start with this curve, and this is what you segment the upper part of the ocean too. So it depends on the initial value. Even I think there are many examples. I think I have a movie. Yeah. So this is very common. This is very common, right? So the slow convergence and dependence on the initial value. So those you see we can overcome those things by some newer techniques. So therefore you see that piecewise constant level set method. So this is essentially you see that so we don't you see the somehow related to the graph cut. Maybe I'm thinking we can skip this part. Also the phase field. I think phase field for people working with material science is very. So we can also skip the phase field. Maybe I don't know. You see that we don't have much time. We should stop here. Yeah. So the convex relaxation, you see that you currently global minimize, you get very easy computation, And so there you see we have a proof, and then I'm going to explain the essential idea of the convex relaxation. And especially you see graph cut, you see I'm going to explain exactly, you see the graph cut, we'll solve this one by graph cut. It's exactly minimum. You see, if you don't regularize, reduce it to the k-mean. Reduce it to the k-mean. And if you regularize, this exactly becomes the Temp model. So there is a clear connection between the graph cut and the Temp model. And so therefore, you see later we found out, you see that you see the graph cut, you don't need to solve it by graph cut. You can formulate it as a convex minimization problem, and then there is no graph and nothing else. Those connections and you see those part is very new, mostly overcomes the difficulty we are talking about. So this part is quite exciting. It's quite exciting. So therefore, hopefully you see that we can go through this part together in a very careful way, such that you understand it. Also, in the end, I'm going to give you the code. So the code is public. You can download it. You can test it, really very, very fast. So it seems that we need to stop here today.
Yeah.
Okay, thank you.